So please let me know if you can see the whiteboard.
Yes, sir.
Okay.
Yes, sir.
Okay. So our discussion is nuclear magnetic resonance. Nuclear magnetic resonance. So before that, we will have to discuss what is meaning of the we just divide this into the few fragments. Nuclear magnetic resonance. We first discuss about this one, nuclear magnetic. So this is a nucleus, okay, and let us say that so these are the let me draw only one. Let us say that, let us assume that this is the hydrogen atom, okay, and this one, the black one, it is the black one is the nucleus, okay, and this red one is the electron, okay, and this one is the proton, okay. This one is the proton, okay. Now you know that the electron is to spin around the nucleus, okay, fine, and this proton, so proton, they do not remain constant, I mean they are not static, they also spin inside the nucleus, because the nucleus is made up of neutron and proton. So this particular proton, it used to spin inside this nucleus. So you know that whenever a charged particle, it starts moving, the moving charged particles always create a magnetic field, okay, that is what we call electromagnetism. If you just remember your whatever you have studied in the physics in the school days, you must have studied about the electromagnetism. That is, once the electron passes through a particular field, so they generate the magnetic field perpendicular to their direction of movement. So this is the Faraday's principle, okay. So now this proton, it is having the positive charge. When it spins inside the nucleus, so it creates a magnetic field. That means this particular nucleus, it is acting as a magnet. So you know that whenever we talk about the magnet, so magnet is to have two poles. So one is called north pole and one is called south pole, okay. Similarly, this particular hydrogen atom, where the proton is spinning, because of which it is acting like a magnet, so this also has the north pole and south pole, okay, fine. Now when you keep this magnet in a magnetic field, now what is this magnetic field? Let us assume that this is a magnet, that is your hydrogen atom, because the hydrogen atom is acting like a magnet because of the spinning of the proton, okay. Once you keep it in the once you hang this magnet, so what happens, this magnet, it used to make a orientation. Orientation is like this, the north pole, used to be towards the northern side, and the south pole used to be towards southern side, okay. That means once you take a magnet, just hang a magnet, your magnet will align itself in such a way that the north pole will be towards northern side and south pole will be towards southern side, Okay, now let us assume that we are keeping this magnet in a magnetic field. Okay, so supposing that this is a magnetic field, okay, and let us assume that this side, it is the north pole of this particular magnetic field, and this side we have the south pole of the magnetic field. Okay, now supposing that we just place a magnet over here in this manner. Okay, so what will happen, this particular magnet, okay, what it will do, this north pole and south pole, we just keep it like this. Okay, so can you hear me? Please let me know if you can hear me. Please let me know if you
Yes,
can hear
sir.
me.
Yes, sir.
Okay, so supposing that the magnet that is placed in this magnetic field, okay, is placed in this manner. So what will happen, immediately this magnet will rotate in this north pole, will rotate in this direction, and south pole towards this direction. That means immediately this magnet will become like this. Okay, so the north pole will be towards this side and south pole will be towards this side. So now this spinning of the magnet in the magnetic field, this is called alpha spin. This is called alpha spin. So alpha spin, something like this, when we place a magnet in a magnetic field, okay, in a irregular direction, so immediately your magnet will orient itself in such a way that its north pole will be towards north side and south pole will be towards southern side, okay, of the magnetic field. So this spinning of the magnet, it is called alpha spin. Okay, so now in this way, this particular magnet is now stable. It is in the stable condition. Okay, now supposing that now you want to reverse this magnet, that means if you want to turn this magnet in the reverse direction, something like this, you want to change this magnet in reverse direction, something like this. So you want to reverse this magnet. Okay, so now what will happen if you want to make this orientation of the magnet in the reverse direction? So what you will have to do, you will have to apply energy. Okay, so that, because what happens when once you place a magnet as such, so this magnet will immediately, it will make an alpha spin, and now this alpha spin will be made by the magnet. You don't have to apply any energy, it will make by itself. Okay, but when you are making it in the reverse direction, this direction, north pole towards south pole and south pole towards north pole. Okay, so in this condition what will happen, you will require energy. Okay, fine. Now how much energy you will require, it depends upon the strength of the magnet. Okay, supposing that you have two magnets here. Okay, so one magnet is a weak magnet and one magnet is a strong magnet. Okay, so now you want to reverse the orientation of strong and weak magnet. What will happen, you will have to apply more energy for strong magnet and you will have to apply less energy for the weak magnet. Okay, so now this kind of spin, reverse spin, it is called beta spin. Beta spin. So alpha spin, the magnet will make by itself. Okay, fine. It will make the alpha spin, so that the north pole is towards north pole and south pole is towards south pole. Okay, beta spin, it is not a I mean to say, it is not a spontaneous spin. This spin you will make by yourself. To make the beta spin, you require energy, because you are orienting the magnet in the reverse direction. Okay, fine. So now how much energy is required to make the beta spin? It depends upon the strength of the magnet. Okay, if you have got a weak magnet, so the energy required will be less. If you have a strong magnet, so then the energy required will be more. Okay, fine. So this is the principle of the nuclear magnetic resonance. So this beta spin, to make a beta spin require energy. This is what is called resonance. So resonance means different magnets you require different amount of energy to make beta spin. This is what is the resonance. Now how we are going to identify the structure of a compound using the nuclear magnetic resonance? Let us see that one. So here the basic thing that is required is the beta spin. How much energy is needed to make the beta spin? Okay, so let us understand in this different way. In case of nuclear magnetic resonance or NMR equipment, so here inside the NMR equipment we have a magnetic field. Okay, where towards one side we have the north pole and towards one side we have the south pole. South pole. Okay, now here we have a compound. Let us say we have a compound, say Cl H Cl C H, then CH. I'll just make this structure. Now this is a compound you have. Okay, fine. The thing is that you want to determine the structure of this particular compound. Now when you place this compound in the NMR field, okay, NMR field means the field where you have the magnetic field. In the NMR equipment, you have it inside the NMR equipment, there is a magnetic field. When you place this compound here, okay, in this field, now you see here what is happening. You have the 2 hydrogen, here you have 3 hydrogen, here carbon, you have a carbon, and this is the chlorine, okay, chlorine atom is there. Okay, now let us talk about this particular hydrogen. Okay, so because the hydrogen, we are considering the hydrogen to be a magnet. Okay, so hydrogen is one, so you have one hydrogen here, and then this is the second hydrogen, this one, CH2 is there, 2 hydrogen. Okay, fine. Okay, then this particular hydrogen, okay, it is surrounded by two numbers of carbon. Okay, so then towards this side, let me change the color. This is one carbon, okay, and this one is the second carbon. I'll make it blue. Okay, fine. Okay, so now this is one carbon, this carbon, and the green one is this carbon. You have 2 carbon here, and you have these 2 hydrogen atom. Okay, so this hydrogen atom, you have 1 electron only, and you have, this is the magnetic field. Okay, now what happens, because here it is surrounded by only 1 electron. Okay, fine. So this proton which is present over here, this proton is having the magnetic property. Okay, that means this 2 hydrogen is acting like a magnet. Okay, but the thing is that this carbon, it has got lot many electrons. This carbon has got lot many electrons. Now this carbon also has lot many electrons. Lot many electrons are there. Okay, now what is happening, these electrons, they are shielding the magnetic property of the hydrogen. That means what happens, that when you have a magnet, you have a this nucleus here, and a proton is there. Okay, so proton is creating the magnetic field. Now outside you have the electron. Okay, now this electron, it shields the magnetic property of the proton. In case of hydrogen, you have only 1 electron. So 1 electron is not sufficient to shield the magnetic property of the proton. That means if you have only 1 hydrogen, okay, independent hydrogen, nothing is linked there. So in that case, the hydrogen atom is a strong magnet. But in this case, what is happening is that you have a hydrogen, and nearby hydrogen you have a carbon. So carbon has got lot many electrons. These electrons, okay, they are nearby the hydrogen. So these electrons, they are shielding the magnetic property of the hydrogen. As a result, the hydrogen becomes a weak magnet. Okay, now you see, once the hydrogen is alone, so in that case, when the hydrogen is alone, so your hydrogen is a strong magnet. Okay, because the nucleus is a magnet because of the spinning of the proton. Okay, but when this nucleus is surrounded by lot many electrons, these electrons, they shield the magnetic property of the nucleus, and as a result, the nucleus becomes a weak magnet. Now in this case, we just go back. In this case, what is happening, the carbon present over here, their electron, because this 2 hydrogen, they have got only one electron. This 1 electron, it is not sufficient to shield the magnetic property of the nucleus. But the nearby electrons of the carbon, they are shielding the magnetic property of the hydrogen atom. As a result, these two hydrogen molecules, they become weak magnet. Okay, fine. That means if you place only hydrogen atom here, so when you to make a beta spin, you will require more energy. But because in this case the hydrogen is linked to the carbon atom, so this carbon atom electrons, they are shielding the magnetic property of the, or shielding the magnetic strength of the hydrogen. As a result, what is happening, these two magnets, the hydrogen magnets, they are becoming a weak magnet. So for this reason, for beta spin, you will have to give less energy. But the story does not end here, because if you see this structure, this CH2, 2 hydrogen, then surrounded by 2 carbon, and it is also surrounded by 1 chlorine atom. Okay, so let me draw the chlorine with yellow. Now this chlorine atom, you know that the chlorine is electronegative. It is more electronegative. So chlorine is more electronegative. That means electronegative elements, they have got the capability to pull the electrons towards themselves. Okay, so this is all these things you must have studied in your school days in the chemistry, that those elements which are highly electronegative, they have got the, because their nucleus is very strong, so they pull the electrons towards themselves. As a result, what is happening, these electrons of the carbon, they will move towards chlorine. They will move towards chlorine, that means they will move away from the hydrogen. As a result, what will happen, this hydrogen again becomes a strong magnet. Because if the chlorine is not there, hydrogen is a weak magnet, because their magnetic strength is shielded by the electrons of the carbon. Now in this case, the chlorine is pulling the electron towards itself. So what is happening, there is less electrons present nearby the hydrogen. So hydrogen becomes a strong magnet. Okay, so that means strong magnet means to make a beta spin, you will require more energy. Okay, that means this hydrogen to make a beta spin, the energy requirement is more. Now let us come to this hydrogen, H3, this one. Okay. Now in this case, what is happening here? You have 3 hydrogen. Okay, and then you have 1 carbon. 1 carbon is there. Okay, fine. Now this hydrogen, they have 1 electron. Okay, fine. And then, but in this case, the hydrogen, they are not acting as a strong magnet, because the electrons of this particular carbon, okay, they are shielding the magnetic property of the, they are shielding the magnetic property of this hydrogen. As a result, what happens, this hydrogen, okay, these 3 hydrogen molecules, they are acting as a weak magnet, because their magnetic properties are shielded by the electrons of this carbon. Okay, now in this case, these 2 hydrogen atom, they are acting as a strong magnet, because their magnetic property is not shielded by this carbon, because the electrons of this carbon, this is pulled away by this chlorine. Okay, fine. So now what happens, when you make a beta spin, so you will require less energy, because this is a weak magnet. You will require less energy to make a beta spin of this 3 hydrogen atom, but to make a beta spin of this 2 hydrogen atom, you require more energy. Now the question comes is that we are talking about less energy, more energy, how you will make the beta spin. Now to make the beta spin, we use the electromagnetic radiations. Electromagnetic radiation. Okay, fine. So electromagnetic radiation will make the beta spin. Okay, because the electromagnetic radiation, they have got the energy. Okay, so now this electromagnetic radiation, okay, you will require more amount of radiation. Okay, you will require more amount of radiation to make the beta spin in this particular hydrogen, and you will require less amount of radiation to make the beta spin of this hydrogen, because less amount of radiation means less energy, okay, to make the beta spin here. Now based on that, okay, so what happens at the end, you will get this kind of graph. You get this kind of graph. Okay, so graph will be something like this. So x-axis, it is the energy. X-axis, it is the energy, and the y-axis, it is the intensity. X-axis, it is the energy. Okay, fine. Now you see the first peak. First peak, what does it indicate? The first peak indicates the, that means this is the peak of, here you see the less amount of energy is used. That means this is the peak for this particular hydrogen. It's a peak for this particular hydrogen because it is a weak magnet. Okay, so weak magnet means less amount of energy is required. Now you get a second peak like this. So this peak is for this hydrogen, because this hydrogen, it is a strong magnet, so you require more energy. Okay, so now what will happen, based on this graph of the energy and how many peaks you are getting. Okay, based on that you can identify the structure of a compound. Okay, that means you have a, say for example, you have a particular compound where you have a carbon, then you have a nitrogen, okay, you have a hydrogen. So in that case, this structure of the peak will be different. That means for every compound, these peaks are different. For example, you have a glucose and you have a glucosamine. If you see the difference between the glucose and glucosamine is that in the glucosamine you have only one amino group. Otherwise, complete structure is same. Okay. So now, how to differentiate? Because chemically you cannot differentiate. So you can differentiate using the NMR. Okay. So NMR, what will happen? The structure of the peak will be different. Glucose will be different. Glucosamine will be different. And say for example, another example I am taking, ampicillin and penicillin. If you see the structure of the ampicillin and penicillin, they are not very much different. Okay, but how can you differentiate? You can differentiate using the NMR. Just take the ampicillin and put it in the NMR machine, and you will get this kind of peaks graph you will get. Okay, so the graph of the ampicillin will be different from the graph of the penicillin. Okay, so this is how this can be used also to identify the compounds. Okay, so you have a purified compound, suppose, okay, and that compound you put it in the NMR. Okay, so then you will get a particular kind of graph. Now this kind of graph, you can just compare that this graph belongs to which compound. Okay, so like you have a yes, the one library is there, so you can using that library you can find out that my graph is matching with the graph of which compound. Okay, so this is how you can it can be used for identification of the compounds, and also it can be used for identification of the structure of the proteins also. Okay, so say for example, you know that some proteins, they are phosphoproteins. Phosphate group is there. You have a two protein, exactly same protein. Okay. Say for example, hemoglobin. You have a hemoglobin, normal hemoglobin, and you have another hemoglobin. There is some abnormality. Okay. Fine. So now you just do the NMR. Okay. And then what you will find is that the structure of the graph of the NMR graph will be different in these two. Okay, fine. So this kind of study, it can also be used to determine the abnormalities in the protein structure. Okay, and also some people, they have also used it for determination of some kind of anomalies in the genetic structure. Say just take out the DNA, because many times sequencing and all is not possible. Okay, so these things, it can be studied here. And say for example, lipid, say particular in the skin, there is some disease condition where there is a difference in the structure of a lipid. Okay, so it is very difficult to identify the